Hi, this is Shelly Physics. I'm doing an episode on determining error in your measurements and calculations. Now, when you measure something, you usually have a measuring instrument like this ruler here. And I've got a measurement in centimeters and millimeters up there. And if I were trying to measure the length of my phone here, I would hold it up and, of course, take as close a measurement as I can. Now, you might be measuring in centimeters. And if you measure this in centimeters, it looks like we're somewhere around 15 centimeters. But with that, there's an amount of like a plus or minus amount. How specific can you get about that measurement? Well, it's all up to the measuring device. If this only had centimeter marks, I might have to say 15 centimeters plus or minus 1, because the exact amount is somewhere in between 14 and 15. So I might write the length of my calculator is 15 centimeters plus or minus 1 centimeter. Okay, or I can write you can write 15 plus or minus 1 centimeter. Either way works just fine. So that's great. What about what if I could measure to the millimeter? If I look really closely and try to do a good job about that. Oh man, there's like this curved case on it. It's hard to tell the edge, like where exactly the edge is. So I do my best with the measurement, and it looks like we're about 14.9 centimeters, or I could say 149 millimeters. But it's kind of in between the marks there. It's hard to tell where that area is. So I might also be able to say the length is 14.9 plus or minus 0.1 centimeters. You see, I'm a little more specific there. I can measure it to a higher precision. And the precision is what we can see by finding the percent error. Like by, comparing 0.1 to 14.9, it's not always obvious how much that plus or minus margin is. So what I can then do is take the 1 centimeter, let's go for the first one, see how precise this is, and divide it by 15 centimeters. You see the centimeters will cancel. We'll bring my calculator up here. You'll see a new view of it. There we go. Just take 1 divided by 15, and we get a percent out of that, 6.67%. There it is. So I could also say this is 15 centimeters plus or minus 6.67%. Okay, so we have you might see that kind of percentage in like a presidential election poll, if they're talking about percentage of voters voting for candidate 1 or candidate 2, that type of thing. Now, what if we look at this number here? We were trying to measure this to a higher precision using millimeters instead of just centimeters. Now, I did measure this in centimeters, but we did get down to the 10th of a centimeter, which is the millimeter. So we can try that. 0.1 divided by 14.9. What is that percent difference in error there? 0.1 divided by 14.9. And look at that, we get 0.671%. So we get 0.671%. Okay, and I'm using 3 digits there because I can measure to 3 digits for my measurement. I'm just keeping a percentage there. All right. So the smaller the increment that we can measure with our measuring instrument, the better. Now, what if I were trying to measure like a length of a table? I might have to use something like a meter stick. And this meter stick can measure to the millimeter. But on long tables, sometimes you have to like lay the meter stick down, and then like you look at the end of it and you go, oh, the table's even longer than that. So I have to put the end of the meter stick where it was, put the beginning of the meter stick where it ended from before, and I get down to a measurement. But I had to like shift it, I had to measure it, I had to kind of move things around. So even though I might be able to measure to the millimeter according to the meter stick, I might go, you know what? This still might be plus or minus a centimeter, or I could be maybe a half a centimeter off. So what if I measured the, we'll call it length 3, so I get some different lengths here. Length 3 of the table. What if I see that it's 1.267 meters See, it gets to the decimeter, the centimeter, and the millimeter. But since I had to do a little shifting, I might go, well, even though this does measure to the millimeter, it might not be a very dependable amount. So let me go plus or minus a half centimeter. I'm pretty sure, I should interpret that here in a second. I'm pretty sure I got it down fairly well. But to make it agree with a meter value, I really should write 1.267 plus or minus, if it's a half centimeter, 0.005 meters. Okay, half centimeter would be 5 millimeters. All right, so that percent error would then be 0.005 divided by 1.267. So this is just functionally how you would record error in your lab measurements. Okay, so at a 0.394%. There we go. Okay, that was just a few different lengths there. Now, what if I want to actually calculate a quantity and have an error from the measured, like, for example, let's take the phone here. I measured the length already, and we'll take the 14.9 plus or minus 0.1 centimeters as the length. Now let's go for the width here. What would be the width of this? Now if I take length times width, I would be able to calculate area. So if there's error in the length and there's error in the width, should there be error in the area? Yes. So let's get a measurement first. I'm getting about 7.8 centimeters. So let's call it width 2 to go along with length 2. Okay, width 2 is 7.8 plus or minus 0.1 centimeters. I'm fairly certain about that width there. So let's get the percent error, 0.1 divided by 7.8. 0.1 over 7.8. And I get 1.28%. See something that did happen here? Just take a look at the length and the width. I can only measure the precision up to a millimeter. Okay, so if I've got 0.1 centimeters or 1 millimeter, compare that to the smaller width and the larger length. Okay, so 0.1 over this larger length gave us a smaller percent error, and the 0.1 over this relatively smaller width, we get a larger percent error here, almost double. Okay, so the smaller the measurement is, the closer it is to that precision increment, the larger percentage error you're going to have. So as best as possible, you tend to try to take the largest measurements possible. When it comes to presidential polls, you poll as many people in a diverse population as possible to get an accurate, closer to accurate probable outcome for an election. So the larger numbers we can get, or the smaller the precision increment we can get, the less percent error we're going to have. So if we were to measure or try to calculate the area, it's going to be, we're going to take length 2 times width 2. I guess we'll call that area 2, just a arbitrary number there. We just multiply the two measurements, 14.9 centimeters times 7.8 centimeters. So 14.9 times 7.8. 116.22. Now I should keep some sig figs in mind. This is 116, so I should, should I say 116.22 or 117? This is all I have, so I've got two significant figures, so I should make this 120 centimeters. Plus or minus what? All right, so plus or minus, I don't know. Like, what goes here? Do we just go back and add up the 0.1 and the 0.1 here? Is it plus or minus 0.2? Well, it's percentage. You see, even though we multiplied a couple of these numbers together, what do we do with the percent error, or what do we do with that margin of error, like the 0.1? Well, statistically, it turns out if you take the percent error of the 4.9 and the percent error of the 7.8, sum them together, that'll be the percent error of the multiple of the two, the product of the two. All right, so what you do here is we're going to take 0.671, which was the percent error from the 14.9. We're going to add to it the 1.28, which is the percent error from the 7.8. We're just going to add those two together. Okay, we got a 1. Ooh, this is old school math. Carry the 1, 9, 1. So we're going to have a 1.951%. Let's apply that to the 120. So now we take the 1.951% times 120, and we're going to get out our margin of error from it. So 1.951, the sum of the 2% errors from the others. And I plug that into my calculator. I'm going to divide that by 100 to get percent. There we go. And I'm going to multiply that by 120. So 2.34. So plus or minus 2.34. And this was centimeters times centimeters, so we should have centimeters squared. There we go. Okay, so keep your sig figs, add your percent errors, and apply that percent error to your answer, and that'll be it. So whether you multiply and divide two numbers, whether you add or subtract two numbers, you're going to add the percent errors. And that's how it works. Okay, I hope this has been helpful. Oh, one last thing. Sometimes you might end up with a square value. What if you've got like a time squared? In physics and motion, that also often happens with an object accelerating. So what if you have a time squared? Well, if you have a percent error for the time measurement and you square that, that means when you square the time number, you also have to add the percent error. So it's got like the t squared is going to have twice the percent error as the single t. So there's a multiplication there. What if you're dealing with trig? Like, what if you've got a couple of measurements here, two sides of a triangle. Ooh, that's an ugly triangle. And let's say this side is 10 centimeters, and this side is 5 centimeters, and you've got a theta and angle here. Well, what would that be? Well, tangent of theta would be 5 over 10. Centimeters, of course, would cancel. Now, if this measurement was like 5.0 centimeters plus or minus 0.1, and this was 10.0 plus or minus 0.1, okay, you'd find the percent errors for those two. But look what you're doing with the 5 and the 10. You're dividing them. All right, so with the 5 and the 10, you would add the percent errors. And I recommend leaving, if you can, leaving it as tan theta. Tan theta is a ratio, 5 divided by 10. So if out of this, of course, we'll get 1/2, 0.5, and there'll be a plus or minus margin of error here. Let's just leave it as tan theta equals that number. And instead of solving for theta and trying to figure out what that is and the error involved, if you can, if your calculation involves a tangent theta, there's no sense in trying to figure out what theta is and plugging it back into tangent. Just substitute 5/10 for tangent theta.